Okay, now I have to allow to share this window. Mm, okay, there is another diagram. I was earlier going through this also. I hope you can see this. Can anybody tell me whether so? There are a variety of PIC microcontroller with PIC 16C configuration, and data sheet I have already shown. We were looking at memory and timer functions, and there used to be additional. So I have got many different resources related to the PIC microcontroller, but some of them are talking about some different PIC microcontroller. Though the basic things are same, still certain parameters are little bit different. Okay. Uh, there is a one document by Tarun Agarwal. So I think, okay, this is the same one. Okay, so if you just this is summarizing the capabilities and the what we say the peripherals or the device which are there in the PIC microcontroller. So RAM, ROM, stack, and other things we have seen. Let us just see what is there in the I/O port. The series of PIC 16 consists of 5 ports such as port A, port B, port C, port D, and port T. Okay, and in case of 16C, 6X, where it is for 61, 61 is having only port A and port B. Okay, so you make sure that this particular let me so for this is not there for 16C 61. Okay, and from 62 onwards there are C port, C port D, and then for the higher number of the processor with extra pins, port E and other ports are available. So this is the one thing. Port A is an 16-bit port that can be used as an input or output port based on the status of the tree set. Now this is TRADOC intelligence support activity register. So each port is designated by its particular code when you want to access it. So that port means now it is considered as a kind of a register and which is attached to the CPU. So you have to access that and you have to enable the port, and then this tree support is there. So this particular trees support is enabling or disabling the activity. Okay, so this will, so to select port A, there are two conditions that you have to satisfy. First one, you have to select the port, and second one, you have to tell the port that now you are receiving or you are um, sending the signal. So this is the thing that one has to do it uh, when we are working with the ports. Okay, port B is an 8-bit port that can be used as a both input output port. Then port C is again 8-bit, uh, that for the additional knowledge input, because the once we see 61 we are looking at, we need not to seriously focus on port C, port D, only for our knowledge purpose, that let us see these are the 8-bit, and operation is decided by the status of the trace C. So all these ports, only port A is the 16-bit, this is 8-bit, 8-bit. Port D is an 8-bit port, acts as a slave port for connection to the microprocessor bus. So when we have a master and slave configuration that you have studied in JK flip-flop, JK master slave, so whatever is the master is doing, the slave is copying that action. So similar concept is used, and this thing is as a uh, port D is used as a slave port. Port E is a 3-bit port which serves the additional function of the other signal, other control signals, uh, function of the control signals to the analog to digital converter. Okay, so for the higher level of microcontroller, PIC microcontroller, this is additionally developed port which is connected to the A to D converter and the other devices. So the question can be, as we have seen in the diagram, that there is always A to D converter and then CCP module and all these things. So when they are there, and in the first version of this particular PIC microcontroller is having only two ports, how the A to D converter is going to work? So thing is that A to D converter is a separate module, so that is being connected with the help of port A, port D, because these two ports are available, and then um the bits of these individual ports are accessible. So it is a bit accessible action by means of which now you can receive or send the data from D to A converter. Okay, but people found out that then the port A is engaged to serve the D to A converter. So it is better that we should have a separate connectivity and separate instruction to do this operation. So port A will be available for the other data transfer. So that action I will show you in some of the reference it is shown. Okay, so you can see now when we focused on only the 16C61, um, the question can be how the digital to analog converter in PIC microcontroller is functioning, right? So we have to be careful that in this case, this port A, port B are going to serve the communication with the D to A converter. But when we have a port E, then we need to have a different kind of programming, right? So as the PIC microcontroller changes, uh, despite of having the similar instruction set, and plus as the number of pin increases, the additional instruction sets are getting added. Our programming has to be modified in accordance with the big microcontroller that we are using. uh, Now when we use a ready-made compiler, somewhere it is mentioned that there is a PIC compiler. So then when you start writing anything and you want to access certain, so it will automatically connect the ports, because the coding is there inside the compiler. Only user has to know how to program the particular PIC microcontroller. Okay. The bus is used to transfer and receive the data from the peripherals to another, and it's they are classified. So here they are giving better we can say distribution of the bus structure. One is the data bus, address bus. Then you will have a control bus also to control the other activity. Right. So it is used only for control bus is either enabling or disabling particular peripheral which is connected. Peripheral here means the part of the particular microcontroller, like memory. You have a RAM, ROM, D2A converter. Okay. So all these fellows need to be controlled. So benefit of that is that even by mistake, if you have some data present, unless and until you the CPU orders that I need the data now, then and then the data will be transferred, and then it will be reset to some other level or some other data can be stored. Okay. So when we think about multitasking, um, certain data or certain things or certain events which are going on in the outer world may be slower than the processing speed, but there are additional preliminary things that CPU has to do or one has to understand. So by the time that CPU is preparing that additional preliminary things, the other peripherals can collect the data, and it can have a lots of data, and then suddenly the CPU can immediately access it. So there is no time delay. Okay. So for that purpose, it is done in a smarter way. There are certain like events, meteor shower. So you want to count how many meteor shower you see in the field of view of some telescope. So how much is the area in the sky that this telescope can focus, and then um, the CCD charge coupled device camera can notify this. Okay, so you have to program it such a way that it is like a motion detection. Okay, so this nowadays this is kind of a AI software, artificial intelligence. Whenever there is a motion, the camera will start automatically recording, and then it will stop. So individual pixel, the series means all the pixels will be having some similar set of light falling on it, intensity, constant intensity, and suddenly the intensity will change at certain pixels. And since all this data is transferred by means of some JPG image or MP4 file kind of thing, whenever there is a change in this intensity, it is assumed as a some activity or some motion, and now this motion has to be uh, measured. Okay, so this way you can do automation of measuring the meteor shower in the field of view of this, and then you have to do some smart program that okay, this is one meteor, otherwise there will be trail of the meteor, and then it will be considered as a so many meteors. So um, by how much what speed they are falling on the earth, so that can be calculated. So uh, now the additional peripheral will just keep on measuring in 1 hour certain events, and then CPU will ask for the data that how many events. So in one, by the time CPU will make some preliminary arrangement, and suddenly the IO ports will send the data. Okay, that some 100,000 counts are there in that field, and then by considering that uh, for a particular area of the sky or for a given city, these fellows can now calculate that okay, in 1 hour this was the meteor shower. When you think about weather broadcast and then a meteorology department, they declare the value of rainfall, right? So they have some set standard that um, they collect the water, and then they say this much of water, this much centimeter of normally of water in a rainfall. So yearly, hourly rainfall, monthly rainfall, weekly rainfall. So all these data they make available. So in such applications, um, all this device can be used. Okay, and so there is a one more bus that you can add here is a control bus. Okay, so role of control bus is to control the operation, okay, or the activate or deactivate the peripherals. So data bus, address bus, and CPU. So you can additionally put this, and you can try to also find out almost in the microprocessor. Also, the control bus is there, but people don't mention. Okay, in the bus structure. Uh, so when you mention it, you have to justify with the help of some peripherals that see this peripheral is there. It has to be enabled or disabled. So that enable disable signal that goes from the CPU is because of the control bus. Okay, it doesn't travel with the address bus or memory bus. And we have seen in my 8051 microcontroller, PIC microcontroller, um, there is a flag register. See, there is a indirect indication of a control bus through the flag register. So when the flag is set to 1, the particular timer or particular port is activated. If it is 0, it is disabled. Okay, and there is some interrupt enable, interrupt disable. So these are all kind of a control bus. These are part of a control bus. So this way we have to justify that there is a control bus in this category. You will have a different and lines which are notifying the CPU or which are controlled by the CPU, where what to do and which device will be enabled, disabled. Okay, even you want to transfer the data. Sometimes what happens that if you don't have control bus, separate control bus, suppose you want to transfer the data, then within the data, enable bit and disable bit, these two bits are sent. So when we talk about 8-bit microcontroller or 8-bit microprocessor, what will happen that uh, so we have some enable bit like this. Then we have our 8-bit data, and then there is a disable bit. So that depends on the active low or active high signal. When it is active high signal, this one will be pass going. This one will go and activate the particular device. Okay, when the address is already fetched, and then this 8 so this data will go into the memory section, and then it will say stop bit. Okay, so uh, this is start. This is serving stop. Okay, and this is the content. So start bit, stop bit. This way it is going to work. A to D converter, I need not to tell you, analog to digital converter. Uh, I hope you have studied a little bit about ATD converter in your TYBSc. But okay, in MSc you have a D2A converter, digital to analog converter. Okay, so what it does is that it changes the analog signal into digital signal, and then it transfers it to the CPU. Okay, along with that you may have a D2A converter. Now D2A converter theory is very easy. I don't know whether you have in your experiment or not. D2A converter has a two types of network. One is ladder network and one is the binary ladder network, and then there is a weighted register network. So From that network, one can convert that analog signal into digital signal into analog signal. Now D2 A to D converter requires D to A converter. That is the funny thing. Okay, so D to A converter is very easy to devise or fabricate, but A to D converter is little bit tricky, and you require D to A converter. So depending upon the value of D to A converter, you will get A to D signal. Okay. So how it works, that I will tell you later on as we proceed further. Right now, you just see that there is a D to A to D converter. Now this A to D converter will have a various bits also. Normally 8 bits, but sometimes in some processor you may require 16 bits. Okay, and the voltage is 5 volt of an analog reference voltage. So uh, all the microcontrollers are designed to work at lower voltages, or specifically the system voltage is 5 volt. So um, 5 volt is now divided into various parts, 2 raised to n parts, in order to facilitate the A to D conversion. Okay, so it will have its own resolution. Timers and counters we are looking every time. So this section, timers oblique counter, is purposely written when we say there is oscillator. Now oscillator can oscillate at a certain fixed frequency, which is decided by the manufacturer. Okay, that means whenever the oscillator is a free running oscillator, it has a maximum frequency, but the capacitor that are connected to that particular oscillator will decide the oscillation frequency of the oscillator. You can have RC oscillator, you can have resonance oscillator also in place of that, but they are not reliable. Crystal oscillator is more stable, and then internally you program it to choose particular frequency. Either you have a maximum frequency or you have a lower frequencies. This is the arrangement. There are interrupts. PIC microcontroller consider 20 internal interrupts and 3 external interrupts. Source like ADC, USART, and timers. Okay. So universal synchronous read and receive and transmit, and timers. So, and because of the analog to digital converter, this is also acting like a interrupt. Now serial communication has got this USART SPI protocol, I2C protocol. So somebody was asking like this, I2C. So I2C protocol stands for inter-integrated circuit, and it is the serial protocol. So which is used to connect low-speed device such as EPROMs and microcontrollers. But this using this protocol, one master can communicate with many slaves or many other peripherals. That is the benefit. And each device will be having its own name or address, right? So this protocol will send and receive with that particular address. Means it is like asking individual to do certain tasks by calling their name, right? So then there is a SPI protocol, serial peripheral interface. It is to for this particular device like SD card, sensors and shift register, you require SPI protocol. And USART is to send and receive the data. Uh, so it is sending and receiving data bit by bit over a single wire with respect to clock pulse. Okay, the PIC microcontroller has two in pins, THD, RHD. Okay, so when it is synchronized, means these two devices are having similar clock frequency. So with the pulse, the data will be bit by bit transferred. If it is not having this thing, what we say, same clock speed, then it has to change the clock which is sent out by the CPU. So there is a timer and control unit that will manipulate the clock, and then it will give you this thing. Okay. Okay. At this moment, we need not to know much detail. Means what exactly happens, how it is communication is taking place. It is just part of the uh, communication. Okay. And within that communication, these are the different protocols, because this will have its own different book. If you want to study all these protocols, then they will have their own books, and then there is different methodology within that. So only we need to know the use of all these protocols, that this is the protocol, and on this protocol the device which work, we have to communicate with that protocol only. So here you can see this PIC microcontroller, TX and RX. So it is transmitter, and this is receiver. Then you have a level converter which convert these levels, and then you have a PC or terminal program. Okay. Oscillators. So we have a clock frequency from 30 kilohertz to 4 megahertz. Okay. So for a particular PIC microcontroller or higher also. So this is being controlled by the frequency will be controlled by uh, the capacitor which are connected to this oscillator. Okay. And then so people keep higher frequency configuration, and then using the internal programming, they apply some sort of a mode counters. Role of mode counter is that it counts the number of pulse, say mode 10 counter, so it will count number 10 pulse, and then it will generate its own clock signal. Again it will wait for the 10 clock pulse to come. So in this way you are dividing the clock pulse by 10. Okay. So this is the one idea. CCP module is capture mode, compare mode, and pulse width modulation mode. So when you have a capture mode, this capture mode captures the time of arrival of the signal, or in other words, when the CCP pin goes high, it captures the value of the timer one. Okay. Okay. So compare mode, compare act like an analog comparator. When the timer one value reaches certain reference value, then it generates an output. Okay. So when the CCP pin goes high, it captures the value of the timer one. When compare mode, the compare mode acts as an analog comparator. When the timer values reaches certain reference value, then it generates the output. Pulse width modulation. This PWM mode provides pulse width modulation output with 10-bit resolution and programmable duty cycle. Okay, just a minute. Okay, sorry for the interrupt. Anyways, PIC microcontroller application. Uh, okay, this we don't need to see. Uh, I think last time we have seen this document where it has all the specification listed out. So this will also help you to tabulate all the things which are available with the PIC microcontroller. Within this document, um, there are a variety of things which are there. So there is a 16-bit instruction word and data is of 8-bit. Now what is inside the PIC microcontroller where I want to focus right now. So it has a program memory which is flash, uh, nowadays available in the PIC microcontroller. So you must have heard the word. Now flash the program into the microcontroller, or even in your mobile phone, flash memories are there. So what you do, you write the firmware by means of some external software using PC, or there will be on the go system. So there is a basic bias which is there in the mobile phone. Then you put some file. Okay, and then you so once you have a zip file, that zip file will be flashed into the memory and then it will boot into that. So there is a called as recovery boot in a mobile phone. So when you go into that recovery boot, you can reset many things, like reset the software to the earlier day. Means you can clear the all contents, additional software, and you bring it as it is. So these things are there. The program memory is where your program resides. Okay, so earlier EEPROM used to be there to write the program, where E means electrically erasable programmable read-only memories. Then there are some role of UV light which can also erase the uh, particular ROM. So for that purpose, you must have seen a IC on a microprocessor. If you observe the kit, these UV erasable ROMs are used. So there is some sort of a glassy structure on the IC itself. When you shine the UV light, it will erase the program. Most PIC microcontrollers nowadays are based on the flash technology, where the memory chip can be erased to reprogram using the programmer device. PIC microcontrollers can have program memories from zero point 0.5 to over 16K. A PIC basic program can have several pages of codes and still fit inside 1K program memory. Okay. The width of a 14-bit program memory is actually 14 bits, and it is interesting that PCs are known 8-bit microcontroller. So here this 16-bit instruction word we have seen, the 14-bit program memory. So what happens? Whatever instructions you give, these are written in this 14 bits program memory. So the program word is of 14 bits. Okay, but the difference is that this microcontroller works, or it processes the data of 8-bit only. Okay, and that's why uh, all the processor, I told you earlier that uh, even though the name means the microcontroller or the microprocessors are of 8-bit or 16-bit, the program memory can be of different bit. Okay, so this difference we have to understand. Okay, our ARM processor in mobile phone is earlier it was 16-bit, then 32-bit, and nowadays it is 64-bit. So here this 64-bit or 32-bit is that the width of the um data, okay, or the input that we have, which is of 64 bit. But there is some thing that came into my mind, that if we have a 64 bit of data, means one pixel is represented by 64 bit, and when we have a 4K or 10 you know 1020 by 720 pixels, so 2 megapixel or somewhere 3 megapixel of image multiplied by 64 bits. So this much amount of data has to be stored. Okay. And therefore it may give some difficulty in reading the data, processing the data. So the speed of the processor has to be very fast. So storing data into 8 bit, or there must be some methodology where you have a 16 bit also should be enough. But then people go for 32 bit, 64 bit microprocessor and operating systems to avoid the unwanted attack. Okay. So some unwanted strings are there. It is not easy to block at 8 bit or 16 bit level, but then 32 bit or 64 bit are capable of that. And the micro controller design is such that it by using hardware itself can disable such data, or it can restart the machine. So when it sees some similar kind of bit is coming for the processing, the hardware switches off the machine, not the software. The antivirus that we keep can destroy that such data, but if it still passes through that, hardware is capable to destroy. So these are the data execution protection protocol which is there in the particular operating system. If you go and check all these parameters, then there is something called a DEP, data execution protection, that is there inside the BIOS. So when you see this, it indicates that if some random data execution is taking place, then the processor will reset the machine. So anyways, these things is there. Then so we have a program memory separate 14 bits, and there is a data memory which stores 8 bit of data. So separation of the program memory and data memory. Now we study or we have seen kind of a RISC and CISC architecture. We have not seen von Neumann and Harvard architecture. So Harvard architecture is the architecture where you have a separate address bus, separate data bus. Von Neumann has a common address and data bus. And also you see here that there is a separate program memory and separate data memory. The program will be stored in a separate memory which is of 14 bit wide, and data is stored in a 8 bit wide data memory. Okay. So you just notify this difference. So this is 14 bit, and this fellow is 8 bit. So once we remember that these are the separate entities. Register file map and special function register. So register file map here is that you have a like graph paper, and it is divided into many square blocks, 1 mm by 1 mm, or for the little bit bigger 1 centimeter by 1 centimeter. You don't know how you are going to use it. Then what you do is that if you are asked to plot some graph, then you divide all this maximum area with the given data. You see the quantity, means either it is 100 or 1000 or lakhs. Accordingly you distribute the graph. Each centimeter represent this, so you scale it. Okay. You write the scale on x-axis, voltage, on y-axis you have a current, so IV characteristic can come out. And then whatever is the maximum range you have, that you first choose, and then accordingly you start from 0 to maximum. So 20 lines, 20 centimeter equal to this and this. So whatever this process is called as mapping, right? Graph paper is as it is. You can have a IV characteristic, you can have a mass and force characteristic, you can have a time and some amplitude characteristic, right? So the graph paper remains as it is, but only these random things are there. So similarly, programmer creates its own map, that when the memory is available, RAM is available, uh, in the beginning, when the processor or this operation start, it will map that this area is reserved for this, and this is hardwired into certain um, EEPROM, where the entire operation is written, right? That whenever the RAM is available, it will be distributed with this, that these are the control register, these are the special function register. Um, then there is a user area and so on. Okay. So this way the mapping is done, and within that mapping, special function register, general purpose registers are fabricated or mapped onto the memory, and then they are assigned particular bit values and memory address values. Okay. So what you have in a special function register, that option register, IO register, timer register, intcon register, A to D converter register. So when we have this timer, option, IO and all these things, why we require register can be a question. So as I told you earlier, there is a control bus. Okay. So similarly, what the microprocessor or microcontroller is going to do with all these register, it has to be notified or registered somewhere. Okay, with the help of a kind of a flag as a common name, where this 8-bit flag register will have certain zeros and one, and by accessing these zeros and one, um, either by the user or by the microcontroller, this controller will know that what I am doing right now. Okay? Or when I am transferring the data, I need to set up some register value to one to enable the communication, and then I have to disable certain, like if I'm sending data out, I have to disable the incoming data. So that operation has to be done. Okay, so role of option register is also given. So this register has a readable, writable, containing various control bits. So what it has, this option register bit is port B pull up enable. Okay, so this, the seventh one, the value written in the seventh one, if it is, so the name of the register or this flag is port B pull up, and then either it can be enabled or disabled by storing particular string. So if it is 1, it is disabled. If it is 0, it is enabled. Then this is interrupt edge detection. Okay, so 1 means interrupt on the rising edge of the interrupt input, or you can program it to the falling edge of the interrupt. Okay, so depending upon the device connected to the interrupt pin, if it is generating the rising edge clock pulse or lowering clock pulse, accordingly the signal will be uh, captured by this particular CPU. But to enable or disable this function. Means there is no enable disable, it is only telling you that now the CPU has to listen to the rising edge or the falling edge. Here you are enabling or disabling the port bit. Then this timer 0 clock source. So timer 0 clock, either it will act like a pulse when it is 1, or it will be kind of an internal oscillator. Okay, so the internal operations will be performed on the basis of this timer 0 clock pulse. Then second is the edge select, either it is higher or lower. Then this P3 is prescaler assignment. Prescaler assignment to the watchdog timer, or uh, prescaler assigned to the timer 0. Okay, so this diagram is there. What happens to the prescaler when you assign the prescaler? Okay. In certain programs where you want to access data from the outside world, the watchdog timer has to be reset continuously in order to disable its operation of resetting the CPU. In that case, you have to keep the prescaler. So prescaler will decide some time that for this much time duration, watchdog timer shall not disturb the microcontroller by resetting. Okay. So watchdog has its own internal timer which is matching with the uh, operation or operation cycle duration of particular instruction. Okay. So if the instruction is executing within this given span of time, once it gets executed, it will reset the watchdog timer. So automatically the time will be extended. Okay. It is like you have a 1 hour exam, and suddenly before the means at 55th minute, somebody comes and says, no, now you will get extra time, 30 minutes. Okay. So this providing the extra time is done through certain reset switch, and this is done by the prescaler. That it keeps monitoring that the timing, and it knows that now the watchdog timer is about to reset the machine. Before that, the watchdog timer is reset itself, so it extend that time by another machine cycle. Okay. If this prescaler is assigned to some timer, then this watchdog timer is free to perform its tasks. So it is a like a positive. It is kind of a, some sort of, you can say, negative loop. Okay, negative feedback loop, and this way it is continuously resetting the watchdog timer. Now prescaler rates are there. So from 2 to 0, this is 000 to all 11. So on that basis, the clock pulse is prescaled. So 1 is to 2, 1 is to 4 means when the clock pulse internal oscillator clock pulse are 2, it gives 1 clock pulse to the program, or 4 is to 1 or 8 is to 1. So this way it is prescale. Okay. So uh, once people know, then they can generate the particular clock operation from this particular prescaler rate, that they divide the second into this many number of parts, 128. So here we don't have 100 and all these things, but nowadays like mode 10, so it is like mode 2 operation, mode 4, mode 8, mode 16, mode 32 counters. So prescaler is actually a kind of a counter which counts, and then it generates its own one pulse. So when the clock pulse are 2, clock pulse are 4 or 8, accordingly it will generate from the prescaler. Then there are IO register that I talked earlier. So port A and port B are the part of 61. So we will focus only on that. The port A is a 16-bit and port B is 8-bit port. Okay, and port A is communicating with the external address. Okay, there is a operation related to trees A and port B. So this is shown as an example. So in this case, we have to read carefully, and you have to just grab the information only related to the port A, port B, not all the ports. Only the operation is shown in some sort of example. This trace is acting like a control. And this is the, we can say, the register. Okay. So the trees B register in the direction of port B pins. What happens that this fellow decides whether the data is going to sent out or sent in through this port, because this port um, function is bidirectional. Okay, but at one time it has to perform only one way data transmission. Either it can send out the data or send in the data. And also within that, there are different pins or the pins from where the data can be sent from or particular pin. Okay, so here you see how it is done. 0 1 2 3 4. So 1 and the first two, 0 and 1 ports or the pins are acting like data receiver, and then 3 4 5 6 7 are acting like a data transmitter. Okay, you see the arrow direction. So when you have a trace B, so when it is 1 1, so actually 1 plus 2 is 3. So, but not 1 plus 2, actually this is a bit enabled. Okay, so to receive the data, this is working in link with this, and this is working in link with this. Okay, when these are 0 0 0, they are transmitting the data. When this trees be control, these two first two are 1 1, means they are receiving the data. So this is bit addressable. Okay, so when these two bits are enabled, they are ready to receive the data. Okay, so the port register with this part will have a received data, and this will have a transfer data. Okay, so this way it is programmed, and now the communication can be different. So you can have a serial communication from these two pins. Okay, then what to do with that data is decided by first pin B will be connected to a 2D converter. So you may get some analog signal, then you want to convert it into digital signal. So again you will have to take help of the prescaler and this watchdog timer reset arrangement, and then you will be able to get the data. So, yes. Okay. Um, so little bit tricky operation is there, not complicated, but TRISB is a control. So it tells whether data has to sent out or sent in. That is the role. Okay. So, this is the PIC basic compiler. This is the software. One can use it on the PC to study how it is going to work. I have not used it anyways, but one can find out on it. This is a timer register. So This is a port register and a timer register. Depending upon the mode used, PIC microcontroller have only one timer and some may have up to three timers. So our basic is only one timer. Okay, this is what I'm continuously telling, so that at least somewhere in your mind it will get stored. Some may have three timers. So our case we want only one timer. Okay, the extension to several timers is similar when we shall see in project. Okay, there are some project in this book. They are discussing the project. I am just going for one chapter. The timer in the peak this. Okay, it is not required. So only you can see how the option register is configured using the prescaler. So 1 is to 2 to 1. Okay. So when you have a 4 megahertz clock, the basic instruction cycle is 1 microsecond. Okay. The clock is internally divided by 4. If you select prescaler rate of 1 is to 16, the counter will increment every 16 microsecond. Okay. So uh, for a particular PIC microcontroller, this is the hidden information that we have got. The clock is internally divided by 4. So some book may not mention the basic reference book, but this is a tutorial book. So in that such books, you will get the hidden information, because otherwise it becomes difficult to track why the calculation is going in this direction. So if you 4 megahertz clock cycle, simply 1 divided by 4 into 10 raised to 6. So that many cycles, that much amount of microseconds will be utilized for a cycle. Okay. So it will be 0.25 microsecond. Okay. In our real world. No, in our world, we say 1 upon 4 megahertz, so it is 0.25 microsecond. And then when we set a prescaler like this, people may tell that this answer is wrong. Why? Because this is not given to us. Okay, so 4 megahertz clock pulse is given. Then the main clock is dividing it by 4, so it is a mode 4 counter. Okay. So when the 4 clock pulse of 0.25 microsecond comes, it converts it into 1 clock pulse. After that, it gives to the CPU. Now CPU will give this signal to the prescaler. Okay, and if you design it for 1 is to 16, then what will happen? That since now the CPU's clock cycle is of 1 microsecond because of this configuration, after 16 clock pulse, it will increment. Okay, the counter will increment. So this is the case that can be there. You people can check if this is there in the 16C61 microcontroller. Okay. So that is like a little assignment to you, that you try to confirm that similar arrangement is there inside the 16C61 microcontroller. So here the diagram. The rest of the things are just information how the scaling is going to be 1 is to 2 or 1 is to 4 or whatever. So only the mathematical calculation that you can do it using calculator. PMR 0 and watchdog. So when you have a timer and the watchdog is a basic element present in 8051 also and in PIC microcontroller also. What happens from this diagram, that this oscillator is divided by 4. Okay, so it works like this. So for the 4 clock pulse, it gives one signal. Okay, and there will be some timer receiving input. Okay, so it is there. Now this is sort of an AND gate or gate to which the signal is coming here to the prescaler. Also we have a different watchdog timer. Okay, so this signal is coming here and there will be prescaler. Okay, so this signal directly going as it is to the watchdog time, the gate, which is sending the clock pulse to the watchdog time, to the watchdog. Okay. And if there is a prescaler, what will happen that unless and until the prescaler time or that particular prescaler time matches with the prescaled frequency, the way we have a f oscillator upon 4, here you can have some t upon, say I design it for 128. Okay, so after whatever is this divided by, so 1 upon 128. So if I devise it like this, frequency, that much delay will be added to the prescaler. So after say 128 clock pulse, it will generate one um, h or one pulse. Okay, so like this. So that pulse is acting like a 1, and then this is also some sort of a 1 here. Okay, so when this 1 and 1 matches, then this gate will generate clock pulse 1. And now if this is triggering watchdog timeout, then by the time that prescaler is scaling all this time, the instruction or some events might have taken place, and therefore the data will be given to the CPU and it will be processed. Okay, but the role of watchdog is that to take care that if the processor runs into some infinite loop timing, so if it stuck in that process, then it has to reset the processor that okay, now the situation is out of control and then we have to intervene. So this is the only thing. Okay, so this clock pulse comes and then um, this goes to the TMR 0. Okay. So this is a kind of a simple justification I want to give you that for us on a black box like this, there are two pins and then we have something called oscillator. Okay, and from that it goes inside. What happens inside is this. Now this is the circuitry here. This is being represented by this. Okay. Okay, so this much detailed information is given related to the timer 0 and the watchdog. You have something here, then this signal goes into some small timer element. Now timer element is having this. Now as you start thinking much deeper, you will realize there is a arrangement of transistor to fabricate gates and registers, and these registers are doing all these things. So ultimately, the transistor, either CMOS or NMOS or PMOS, uh, they are used in such a way that they will act like register, or they will act like gates, or they can also give the unstable multivibrator signal. So or it can be fabricated into monostable multivibrator. And these basic elements you have studied from your F5BSc. The individual elements that you have studied, only combination of all these elements in a smart way gives rise to a smart processor. Okay, and this is called a very large scale integration, VLSI technology that we see. So large scale integration, small scale integration. So this is there. Okay, Now this part, overflow time and all these things, I am not interested to uh, show you, because this is kind of additional knowledge. So this part you can try to understand. Okay, you will have to go into much detail, because some confusion it will bring. Overflow time equal to 4 into T oscillator into prescaler into 256 minus TMR0. So 256 is the maximum prescaler ratio that you can have. So all these parameters are sort of a technical knowledge required to program the processor or microcontroller when you are interested to do that programming. TMR1 and TMR2, uh, these are the different counters with two 8-bit register, which are termed as TMR1H and TMR1L. So total 16-bit timer, but has a two parts, high and low, and then these can be separately configured, and the desired operation can be uh, carried out for this. Uh, so they have their own additional role, and since we are sticking to the 61 with only TMRR0, we will not go into much detail of that, but at least you can read it for your interest. Intcon register, it is an interrupt control register. Okay, so if you see carefully, the many people, only 47, so 46 people are there. That also many people are joining very late. Intcon register, interrupt control. Okay, so I'm just pointing certain things, and you focus on it. We have studied timer control and all these things. In a microprocessor, there is a direct communication. Okay, there are different interrupt. They have a different hierarchy, and there is no enabling the interrupt or disabling interrupt kind of operation. Okay, so what happens that the basic model of microprocessor, when the interrupt comes, it will directly jump to that particular interrupt, or it will reset the machine. Okay, and what happens that if every time such interrupts will come, unnecessarily the program will reset, and thereby it will delay, or it will hamper the operation, the desired operation. We don't want this situation. This is the difficulty that people have faced. So there comes this enable disable latch concept, and now the idea of flag register is expanded. Okay, so in microprocessor you have these interrupts are there, and somewhere there is a flag register. What this flag is telling you: auxiliary carry sign 0. So this flag is indicating what is the status of the data. Okay, now let us see the difference in the microcontroller. This is MUT microprocessor. We have an interrupt, but these are controlled through a register. So we have interrupt, then there is some signal control, and then okay, so we have interrupt, any kind of interrupt, then this is control, then it goes to the microcontroller, and we will have now set of register. We have a set of flags. This is there. Okay, and along with this you will have okay, let me just make sure that particular register and the state of the register is also notified or to this. Okay, so this is one kind of arrangement. So this is a flag, or we can say flag bit, and the register. Okay, flag bit and the register associated with it, and then it is going to do all these things. So when we have a port, then it has a port register, okay, and the flag. So unless and until you enable disable this flag, the register is not getting activated, and then the data will go out or in through the register, okay, and then it will communicate. So this is a sort of a kind of a safety mechanism which is utilized in the advanced version of the microcontrollers. And this is a kind of a difference. When I can ask question, what is the difference between the microprocessor, microcontroller, and the microcomputer? So while learning, if you just remember little part of the microprocessor, you will come to know that see, this flag register is playing in some role. That is what we are studying here. Like this, in case of this particular timer 0, so you have a timer to output post scale bits. So these are the select bits. Okay. So if these bits are not properly, assigned 0001 combination, what will happen? That this device is not going to work, or it will work in a random order. Okay. So now the programmer has to know that uh, when we are going to communicate with the external events, then how much time scale will be there, or because everything works on the clock pulse. So first you have to think about the time scale. In that time scale, uh, uh, how many clock pulses are going to be utilized, and according to you have to scale the clock pulse, and then you have to notify into the flag bit, okay, here. Then the register will work, and since this feedback mechanism is also providing information to the microcontroller, it will also wait for that much time. Okay, in this pre-scaled or post-scaled flag, so 1 is to 16. So when this happens, when the event comes, after the event comes, the register is going to notify through some other flag to the microcontroller, and then microcontroller will receive that data, or it will receive the signal. Means the register can be communicating to the microcontroller, okay, through this channel. Okay, so flag bit, you set the flag bit such that you know that within this time scale the signal is going to come. Then this internal clock pulse will keep on ticking on its own. The register will receive the data. After the register receives the data, it will send the interrupt signal. That interrupt signal is also passing through some control, if that control is enabling the interrupt from the register. Okay, sorry, from that, okay, particular timer register or some serial input output port or A to B register, and then it will give microcontroller the instruction that the data has arrived, and then it will take the data, because this particular control is also kind of a flat. Okay, so this is going to work in this fashion. Okay, so um, this kind of a flow one should have in mind. This is going to happen when the microcontroller microprocessor is microcontroller is going to work on certain programs. Okay. So um, initially what we do, we learn only simple operations where we do add, subtract, multiply, divide, the mathematical operations. Then second stage is just transferring the data from one side to other side of the memory. Then we are not trained to work with the interrupts. Okay, we are not trained. Then there will be next level of programming is that you have to uh, just communicate with the other peripherals. Okay, like 88 8080 D2A converter to create sine wave or square wave using microprocessor, communicate with the computer, serial data in SOD and SID, serial input data and serial out data. That is the function. So you have to communicate with the computer. Okay. So in the advanced stage, we should see that we write the program and we wait for certain events and then we notify that event. Okay. So up to that level, once we go, then we are more familiar with this particular program. Either you work with microprocessor or microcontroller. Once you do it, you will see that everything is easy. Even using computer also, you can do many things. Earlier, students in MSc used to program the parallel port of the computer using C language, and this parallel port is connected with some diac or track, and then they can control the fan or tube light in the house. Okay, so this is like a house automation in terms of electricity. So individual pin of that particular printer port, parallel port, is utilized to control one of the device. Okay. So and many students have done this programming. Nowadays you don't see any parallel port present in the computer. So you will have to either use USB controlled, means external arrangement, where you have a USB you plug in and then it will have a parallel port output. And diac track requires only trigger. So with 5 volt of trigger it can work. Okay, or you can have a like fan control. So then you can have some D2A converter, and then it will have a different voltage levels, and with that voltage level the diac track will fire, and then it will control the speed of the fan. Okay. So up to that level people have gone. Now you will see many devices are coming out which are controlled by Wi-Fi using mobile phone. So some bulbs are available, LED bulb, where you can change the color, you can do something and so. So as the technology is growing up, people are implementing the same ideas. Only the technology is different, but the logic is remaining same. That is the important thing. That is what we have to study. That how we can utilize this. Okay. So I will take this A to D converter and then I will stop. Um, For that purpose, I will have to use blank this thing. So how the A to D converter is working, that is what we have to see. So A to D converter register, first we see how it is connected. So this is a multiplexer, but actually this is a pin out of the port that we have seen earlier. Port B. So okay, so there is a multiplexer, and which is this port? It is here. Okay. You see these are the port B. Okay, so you consider, suppose this is a port A, then all these are the pins, output pins of the port B, that can be configured as a in or out. Okay, so suppose these pins are configured for the data in. port B using this trace B. So what you will have to do, you have to make all the pin 1. Okay. Now then you have to channelize that particular port here. So we have seen 16 bits. So for timing, we will take this and 8 bit suppose. Okay. So this is port A. This is talking with the external wall. Okay. Now all these pins are configured to get the signal from 8 different input source. At a time you want to use only one. So this is channelized through the multiplexer. So this is a box called as multiplexer that you are going to study. Okay. So now you see from the port A, any one channel is sending the signal. So all the channels are getting the signals. You program the multiplexer such that at a time it is going to send only one analog signal that is being received by the A to D converter, and then this signal is going to the microcontroller. Okay, so then you will have, okay, so this is a kind of a A to D converter operation. Okay, and to utilize this A to D converter, there is a bit definition. A to D converter. So when the flag associated with the A to D converter is here, okay, so it will have its own control system like this. Okay, and it is a 8 bit. So uh, pin number 7 to 6, what they do, it do the A to D converter clock select. Okay, so there are 4 arrangement: oscillator by 2, oscillator by 8, oscillator by 32, and internal RC oscillator. Then pin number 5 to 3 is channel select, means this it is going to select. So it is controlling the multiplexer also. 0, 1, 2, 3, 4. So at a time only one channel will be selected. Then there is a go and don't bit. Okay. So one is start the conversion, and this is A to D conversion is complete. Okay. So this bit will continuously set reset. Okay, and the CPU will monitor all these operations. This is not in use, and this is the control for turning enable or disable the A to D converter. Okay, so I think this is kind of a operation which is there. Now A to D converter I will show you right now. Anyhow, what is going to happen is that, okay, let me just think, because I am also it is somewhere there is some input which is analog. So analog signal is coming and we want to convert it into D to A converter. So this signal is going through some device. Then what happens? there is a D to A converter, and there is a analog to digital converter. Okay. AND gate is used to have a clock pulse output. Like this. So analog signal is coming, we want digital outputs. I will just try to make some boxes here. How the digital signal come out is that there is a counter. Okay. I have to erase this. So this is digital out signal. Okay. And, okay. So this is clock pulse. So role of the counter is that it has to count the clock. Okay. When signal is coming, I have to think how it is working. And there is a one fixed clock. Okay, so it continuously, but it works according to the signal of this. Now, there is a D2A converter. Okay, I will delete this. This analog signal goes into op-amp. And this op-amp is fed. So this is plus, and this is minus. Okay. Now we have a D2A converter. It is scaled with some signal. This D2A converter its analog output is also fed to the op-amp, and this all I'm just going to show. So this is D2A. So this is a digital signal. Okay. And this is from the clock pulse. Okay, so it has a predefined frequency. This is digital to analog signal, and you see the complicated operation. Now this digital to analog converter has some resolution. So um, maximum voltage is up to 5. Okay, and this analog signal should be from 0 to 5 volt, because it has a internal configuration of 5 volt. In that process, this fellow is setting only 1, means 5 volt signal. So what is happening, that uh, some analog signal comes, suppose of 3 volt or whatever. Let me just do it. Okay, and there will be some reset pin additionally to reset these fellows. And this. Okay, this is okay. Now let us see how the A to D converter works. First, you give some signal at the analog pin more than 0 volt. Now, what is the role of op-amp? Here it is not digital, it is an analog system. Op-amp, anything above the this value, okay, since it is reset, it is giving 0 volt here. Op-amp is like a converter, and it has a 5 volt and below. Either you can keep minus 5 volt if you want to have a bidirectional operation. Okay, we have a habit of getting plus 12 minus 12. Okay, so it is working plus 5 minus 5. So any voltage above 0 volt comes because of the comparator operation. This gives you very high value, 5 volt. This 5 volt is fed to the AND gate. Okay, so AND gate states will be decided by the clock input only, because it is 1. So this clock is deciding the signal. So this clock pulse is going like this. It has nothing to do with this. This is always 1. Okay, when and that time immediately the counter will start from 0 0. It is up counter. Okay, so 0 0 to 1 1. This way it will start working. So all 0 0, so 1 1 1. So whatever is the state of this clock, same is given to the D2A converter. Okay, so what will happen, whatever digital input comes according to the resolution of this D2 converter, which is matching with the up to 5 volt, means number of 2 raised to n, that will be the resolution. Okay, so it will have a 2 raised to n values from 0 0 to 1. So from 0 volt, so 2 raised to n minus 1 values we can say of voltage, 2 raised to n minus 1 states. Now minus 1, because 0 is 1 state, that is not so that will, this many voltage values will be there. So this clock is ticking. With each clock pulse, counter is raising the digit here, signal here, digital, and this is given to this D2A converter. So the voltage is going from 0 to high. Okay, when the voltage level reaches to this value, analog value, within that time span, it is very fast ticking clock. So what will happen, when these two values matches, this will send signal 0. This is going to become 0 now. The moment is become 0, nothing will fade to the clock. The counter will stop. Okay, and when the counter will stop, it will store some value at the output here. Okay, also when the counter will stop, the same data is here, so this value will be hold in this circuitry. Okay, as long as this analog value changes and these two pins are reset. So what will happen? This will be output. Okay, so this is a kind of a operation of analog to digital converter. This is A to D converter. I am not able to uh, draw it properly, but I hope you can just see op amp, D to A converter, AND gate, clock pulse, and counter. You will have to remember all these ingredients. It requires D to A converter, op amp, AND gate, clock pulse, and counter. 1, 2, 3, 4, 5. Okay, this 5 device makes A to D converter work. D to A converter, only one box and some resolution. So there will be uh, many digital input and then resistors with some ladder network and this fellow, sorry, op amp, which will take, it will have its on something and this output. Okay, so that is the difference, that when you want to fabricate analog to digital converter, you require this op amp itself and the uh, D to A converter, means this machinery inside this. Okay, and then it works. So this is the kind of thing. I think I will find out the proper diagram. Means same only the very well drawn diagram, and then I will just post it. Okay, but the operation is very simple. You have to understand, you have to start from the analog input where the comparator is comparing the signal. Since this input is very high, it saturates to high level. This is like a Smith trigger. Okay, op amp is working like comparator or Smith trigger. The moment the input value changes and with this reference, it will either go very high or very low. When it is negative, this is like 0, and this is instantaneous reaction. Whatever is coming, it will immediately switch to the higher value. It has only two states now, very high or very low, negative. So that is being taken as a digital input by the AND gate, either 1 or 0, and it will enable or disable the clock pulse. So this is acting like a switch, okay, depending upon the status of op amp. So this clock is coming here, the counter is starting from 00 to 111, and this same data is given to the D to A converter on the scale of 5 volt. Okay, so with each clock pulse, the values, output value of the D to A converter is rising by the resolution or the value of LSB, lower significant bit voltage. Okay, so it is rising from 00 to 5 volt. When the voltage matches with this voltage, immediately the state of this op amp changes from 1 to 0 or negative, and then it disables the clock pulse. Okay, so this clock and this AND gate is acting like a clock pulse. The moment it stops, the counter will stop increasing its count. Okay, and it will stop there. So whatever is the counter, it is digital value only. Okay, same value comes here, so this voltage level remains stable because the clock is stopped. Okay, so you have to make the arrangement such that the clock pulse going to the counter stops and it freezes the entire circuitry. Okay, and this digital output goes to the particular microcontroller here. Okay, this A to D converter, and after that it will process it and it will reset this fellow simultaneously to receive the another analog signal. So this is all about the operation. Okay, I'll stop recording.